canonical quantization. Of the Klein-Gordon field. So today we'll stick to that particular theory, and over the rest of the week we'll learn how to generalize what we do today, which is so the Klein-Gordon field is an example of a free theory where there's no interaction, so that will make things simpler today. And then the rest of the week we'll learn how to generalize that to interacting fields. So we did most of the hard work in quantizing the field yesterday. So all that's left is to promote our field and its canonical momentum to operators in exactly the same way you'd expect based on the analogy with classical particle mechanics. So when you're doing quantum mechanics, you start with classical particle mechanics theory. To go from particle mechanics to quantum mechanics, you promote the generalized coordinates and their canonical momenta to operators that satisfy the standard commutation relations. So I delta AB, we have several generalized coordinates. And remember, here I'm working in units, where h bar and also c, which doesn't appear in this equation, but will later, are equal to 1. And the q's and p's, of course, all commute among themselves. Okay. So you're all familiar with this process. And we want to do exactly the same thing in the quantum field theory case. So for now, I'll work in the Schrodinger picture. We'll talk about the Heisenberg picture later in the lecture. So the fields play the role of the generalized coordinates, and pi were their associated conjugate momenta. And so just like we would do in quantum mechanics, we want to promote, sorry, this should be phi. We want to promote these classical fields to operators that satisfy commutation relation. Just I, and this Kronecker delta now becomes a Dirac delta. And the field operators now, and the pi's all commute. So we have commutator of phi of x and phi of y all vanish. Okay. And so yesterday, yes? These are spatial positions, right?
So are you saying anything about time?
So here we're working in the Schrodinger picture. So our operators are time independent. So this is all in the Schrodinger picture. And if you remember the analogy from yesterday, we can think of phi of x as like q with a continuous label instead of a discrete label. So this here, this label is just over the spatial positions, not over the space-time positions. So time plays a special role in the canonical formalism. That's why we needed yesterday to check Lorentz invariance, and at several points today we'll be discussing Lorentz invariance because it's not immediately obvious from what we're doing that we're not destroying Lorentz invariance. Time is playing a special role here. Yes?
So this relationship change on Heisenberg picture?
Yes. So these here are Schrodinger operators that are the operators here are time independent and the states evolve with time. We can about halfway through the lecture, I'll discuss the Heisenberg picture. Okay, so one of our main results yesterday was the solution to the classical Klein-Gordon equation. And what we found is that 5x is this integral And so what I've done here is taken our result from yesterday and evaluated it at t equals 0. So this is our result from yesterday. With t equals 0. And if we promote phi to an operator, that means in this equation, we also need to promote A and A dagger to operators. So these were functions yesterday. These were just arbitrary coefficients that we couldn't determine when we solved the Klein-Gordon equation if we didn't impose any boundary conditions. So these were functions in the classical theory. So the functions A k and A dagger k. Now in the quantum theory, become operators, and I'll distinguish them by writing, instead of A of k, I'll write A sub k. And similarly, A dagger sub k. These are operators. Now the commutation relations of these operators, which we'll see in tutorial tomorrow, create and annihilate single particles with definite momentum and energy. The commutation relations between these operators are determined by these commutation relations. So if we just plug this relation in here, we can determine the commutation relations. And you're going to do that tomorrow in tutorial. I won't go through that in lecture now. But I do want to discuss the results a bit. So what you'll show is that AK, commutator of AK with AP dagger, is 2 pi cubed 2 EK times a delta function. And the AKs all commute among themselves, as do the A daggers. So AK with AP is 0, as is A dagger K with A dagger P. So you'll show this in tutorial tomorrow. And you can also plug the same expression into the expression for the Hamiltonian we calculated yesterday. to get the Hamiltonian in terms of these creation and annihilation operators. And the result is, again, you'll show this in tutorial later, d3k over 2 pi cubed 2ek times ek a dagger k ak plus ak dagger. And so this might look somewhat familiar. So if we just look at a quantum harmonic oscillator, we have the Hamiltonian looks like omega a dagger a. So what we have here is basically infinitely many decoupled harmonic oscillators, because there's no terms in our Hamiltonian that mix together states with different values of k. Right, so that this Hamiltonian is diagonal in k. There's no terms that contain different values of the momenta mixed together.
Question, please?
Yes?
I'm just wondering, the EKs, are they the same?
What do you mean?
The EK are the numerator or the denominator? Is it the same equation?
H, yes.
In this?
Yes.
This is an integral over the 3 momenta?
The EK.
Okay, so we're having the same term.
Yeah, yes. So we could cancel this out. I've just left this in terms of the Lorentz invariant measure. So this factor here is going to occur over and over. This is the Lorentz invariant measure we showed with Lorentz invariant yesterday. We'll have different factors here when we look at different operators today and later in the week. So we could cancel it out, but I just like to leave this thing together.
Also, EKs will be different for every K, right?
That's right. Yeah. So EK here is defined the same way as yesterday. So this is EK is equal to root k squared plus m squared. Okay. So what are the states of this theory? So the simplest state is the vacuum. So we'll denote it by 0. And the vacuum is the state that is annihilated by all of the annihilation operators. So this AK acting on the vacuum is 0 for all k. And we'll assume that it's normalized. So we'll just set this equal to 1. So that we can take this as the definition of our vacuum. So what properties, other properties does the vacuum have? So one question we can ask is, what is the energy of the vacuum? So we can compute the eigenvalue of the vacuum state. When we act with a Hamiltonian on it. And so this is the ground state energy of our theory. And we can compute this just by acting with H on 0. And so to do that, we get so there's two terms here. But this first term is 0 because AK acting on 0 is 0. So once we act with it on the vacuum, there's only one term left. So we get this term here, AK dagger, AK, acting on 0.
Just a bit of a notational confusion. The EK bar or EK vector and E0. Here the 0 refers to the vacuum. Does it also refer to 0 momentum?
No, this just refers to the vacuum. Let me call it. Let me just call this E vac.
E dagger.
Dagger is on the right place. Thank you. Okay, so we can compute this using our commutation relations. So if we do that, we commute these. We get a factor of 2 pi cubed 2ek, which conveniently cancels out our denominator here. So we're left with integral d3k ek times this delta function. It's delta of k minus k. Okay. So what have we found? So first of all, this is a delta function evaluated at 0, which is not well defined. It's divergent. And we've got an integral over energy. And so ek for large k goes like k. So this integral seems like horribly divergent. So what we found is evac is infinity. Okay, so let's try to understand what's going on here. Did we make a mistake somewhere? And if not, what's the physical interpretation of what's going on here? So in fact, there's 2 different divergences here. One coming from the delta function, and a second one coming from the integral over the energy.
Then,
Yes.
how did we get the delta function?
So that, when I went from this one, put this down. When I went from this line to this line, I used the commutation relation. So I switched the order of AP dagger and AP, and I got a term that is the right-hand side of that commutation relation up there. And after I switched them, we have an A dagger on the left and an A on the right, so that the switch term annihilates the vacuum. So this is just delta of k minus k. Okay. So 2 different divergences going on here. And the first one is known as an infrared or IR divergence. This is the one associated with the delta function. So to understand where this divergence comes from, let's imagine putting our theory in a box of size L. Okay? With periodic boundary conditions. Okay, so we've got a factor here of delta of 0. Let's try to understand where it comes from. So I'm going to multiply things by 2 pi cubed for a reason you'll see in a minute. So we can write this as the limit as L goes to infinity of integral over our box of e to the I x dot p evaluated at p equals 0. So if we compute this integral, we just get a delta 2 pi cubed times a delta function of p. And then if we evaluate at p equals 0, we get the left-hand side over here. But we can also take the limit p goes to 0 first, in which case we just get this integral, which is just, this is just the volume of our box. So this is just the volume. So we can think about this delta function divergence as coming from the fact that the question we asked is what is the energy of the vacuum, not the energy density. We asked what's the total energy of the vacuum, and if space is infinite, it's not surprising that we got infinity as our answer. So perhaps a better question to ask is what's the energy density of the vacuum. So the only way we would get something finite, if space is infinite, is if the energy density was 0. So we asked kind of a bad question here. So let's compute the energy density. So let's call rho vac evac over v. And using identifying this factor here, 2 pi cubed delta of 0, as the volume of space, that gives us integral d3k over 2 pi cubed ek as half, as the energy density of the vacuum. This is still infinite, so the problem is still there. But this infinity has a different origin. So this is what's known as a UV divergence. And the reason that this integral is infinity is because of the large k limit. So there's no problem near k equals 0. We can integrate from, if we put this in a sphere in momentum space, we would get a finite answer, no matter how big the sphere was. So if we put a cutoff for large k, we can get a finite answer. So we got infinity basically because we trusted our theory to arbitrarily large momentum, which is maybe not the most physically reasonable thing to do.
So they're just putting an infinity there because ek will be infinite at k goes to infinity.
So for large k, the integrand goes like, we could move into spherical coordinates. So rho vac goes like integral k squared dk. And for large k, this becomes like k. So this is like dk times k. So it's like k cubed dk. So this diverges when the magnitude of the 3 momentum is large. So we shouldn't necessarily trust our theory to arbitrarily large momentum. In particular, we're demanding that, or we're studying a theory in a fixed Minkowski background. So at some point, gravity might become important, and we might not want to trust our theory, say, beyond the Planck scale to be very conservative. So we can't trust our theory to arbitrarily large K necessarily. So our theory might break down at some scale. Some scale, big lambda. And we'd expect this is less than or equal to blank scale. Okay, yeah, so we got an infinite energy density, basically because we had infinitely many independent harmonic oscillators, and we trusted our theory to arbitrarily large momentum. But there was an ambiguity when we computed h. So notice that the last two terms here are the same, up to an ordering. So this result depends on the particular order of the classical fields we wrote down yesterday. So at the end of, or in yesterday's lecture, we found that the Hamiltonian was an integral d3x of a half pi squared plus a half m squared phi squared plus a half rad phi squared. But this is exactly the same classical theory as this theory, where I just change the order of these classical fields. So I can write this as a half pi, say, plus I m phi, pi minus I m phi, plus a half grad phi squared. So if we quantize this theory, our operators would be in a different order. So there is some ordering ambiguity in going from the classical theory to the quantum theory. And this result is, in some sense, an artifact of that ordering ambiguity. So there's two ways we could fix this problem. One is we could just add a constant to our Hamiltonian that won't change any of the non-gravitational physics if we just took our classical Hamiltonian and added a constant to it, specifically tuned to cancel this off. Alternatively, we could just start with a different ordering of our classical fields, and we get a quantum theory in which our quantum operators had a different order. And so we'll take the second perspective and just normal order our quantum Hamiltonian. So we're going to find the normal ordered Hamiltonian to be the integral d3k over 2 pi cubed to ek, ak dagger, ak, where this normal ordering symbol just means put all creation operators to the left to the left and all annihilation to the right. And so we'll define all of our operators with a normal ordering symbol.
Dan,
Yes?
I didn't understand when you talked about the ordering. there.
Okay. So these two Hamiltonians are classically equivalent. If we just multiply these two together, we get back these two terms. So classically, there's no difference between the expressions I wrote down on the left and the right.
You're saying the ordering of phi and phi.
The ordering of, right. So here, in this one, we have, if we expand this out, we'll have a phi pi minus a pi phi term. Classically, we can cancel those out.
Okay.
There's no problem there.
Oh.
But once we promote things to operators, we can't cancel out phi pi minus pi phi, because they're operators and they don't commute.
But till now, whatever we did, we just used only this left form.
Starting from this,
Yeah.
you get this operator, this ordering of the operators.
Yeah. We didn't break it down into that form till now.
We didn't break it down into this form. I'm just saying, so this formula gives you this, this formula here. We could order the classical fields in a different way, and we get a quantum theory that's the same as this up to some ordering of the operators.
So here it will depend on how you define your Hamiltonian based on your Lagrange.
That's right.
And how do we fix the definition? We can choose any.
So we're going to use this definition. Here, where all of the operators are normal order. Okay. So that's the vacuum state. What are the other states of our theory? So states of particles can be constructed from the vacuum by acting with the creation operator on the vacuum.
So you're saying that if you now measure the energy of the vacuum with this new H, then it's 0?
That's right. So if we take the normal ordered Hamiltonian and act with it on the vacuum state. Yeah, let me write that down. So if we take the normal ordered Hamiltonian and act with it on the vacuum, we get 0 because there's no term, well, just because this AK acting on the vacuum is 0.
Why is it okay to just say the energy is, I mean, the Hamiltonian is this now? It seems arbitrary.
In some sense, it is arbitrary, but we can't, if we're doing non-gravitational physics, which is all we're doing right now, we can't measure the absolute energy. We can only measure energy differences. And the difference between this normal ordered H and the H we started with is just a constant. It's an infinite constant, but it's still just a constant. So we're not changing the physics by doing that.
One way I'm thinking about why we're allowed to do this, and maybe this, I'm just saying this out to see if it makes any sense, is we're just kind of imposing these commutation relations on what was earlier classical theory, where everything did commute. So could you just say, like, we got this H, we haven't imposed any commutations relations yet. We commute the last ones for free because they're just numbers, and then we impose the commutation relations? Is that?
Yeah, we could. We could come up with a classical Hamiltonian just by adding and subtracting things like pi phi and phi pi.
Yeah.
To get exactly this.
Yeah.
So there's some ambiguity there, going from the classical to the quantitative.
And so when we say that there's a ordering problem, so if we start off with a different order, what do we end up in this edge here?
We would get something the same as this, except we would get some constant here, say C, and some other constant here, 1 minus C.
Can it?
Does that answer your question?
I don't see how that comes.
Okay, so if we look at this thing, this expression here, we can write this as d3x half pi squared plus half phi squared plus half I over 2. There's an m here. And then m here. Pi phi pi minus pi phi plus the other term. This term here is 0 classically. If we promote these to operators, this is just the commutator. Pi, pi, right? So this is not 0.
So you get I delta x minus 1.
Yeah.
And what leads to the other order? I mean,
So what leads to this one? So this is just a convenient choice. It gives us this property, which is
okay. So in a sense, the normal ordering definition that we are writing, that is derived from this condition. We demand that.
This is a convenient property to have. Yeah.
And I'm just wondering, because normally in quantum mechanical system we have a ground state energy, so we are just rescaling that to 0.
Yeah. We can think about this as either just adding terms like that to cancel out the energy, or because we're doing non-gravitational physics, our system is the same if we take our original Hamiltonian and add a constant to it.
For example, like in the harmonic oscillator, you have a half h cut omega.
Yeah, and that's essentially the origin of that infinity we had up there, because we had infinitely many harmonic oscillators.
So it kind of contradicts our basic quantity. I mean, how can we have the ground state energy here as 0? Because
I don't think it contradicts it. It just, nobody has ever been able to make use of the 0 point energy of a harmonic oscillator. So you're just throwing it away.
So in a sense, we are just rescaling it.
Yeah, exactly.
We're just rescaling the infinity to 0.
You're subtracting the 0 point energy of every harmonic oscillator in momentum space. 0 point energy of every harmonic oscillator, which happens to be an infinite.
Yeah, but that doesn't make sense.
Yes.
So we could fiddle with our classical Hamiltonian by adding any arbitrary function of the commutator.
Right.
Right?
I mean, it's the same as saying that we're scaling an infinity to 0.
Is this choice unique that gives us 0 ground state energy?
Is this unique? Yes, yeah, it's unique. So there's only some particular coefficient we'd have to add in front of that term. Just like there's some particular constant we'd have to add we wanted to cancel it out by adding a constant.
So Dan,
Yes.
we always hear about like vacuum energy in quantum field theory, and I understand you got like this whole thing with the 0 point energy, and then you've also got the idea of like spontaneous creation of particles out of the vacuum.
Right.
Those are two completely separate things, right? Am I correct in saying that or not?
So here we're looking at non-gravitational physics.
Yeah.
So if we couple things to gravity, then we do have to worry about this problem.
Okay.
And the answer is not known how to deal with that. So you can think of that as a cosmological constant problem. Okay. So about to talk about the states with particles. So we can create particles by acting with the creation operators on the vacuum. And the one particle states which I will denote as K, are just the states where we act with one creation operator on the vacuum. And as you'll show in tutorial tomorrow, these states have energy EK. And momentum K. So let's look at the overlap between the state P and the state K. So this is just 0 AP, AK, dagger, 0, which, using our commutation relations, is just 2 pi cubed times 2 EK delta P minus K. So one comment to make about this result is that they're not unit normalized. We have this extra factor out here. But if you remember, we introduced these factors of 2K in our measure to make things Lorentz invariant. So this is known as the Lorentz invariant normalization. About half of the textbooks use this normalization. The other half choose a unit normalization where this factor is missing. So that's something you should be aware of if you're looking at, in particular, some of the references I put on the wiki. This is known as the Lorentz invariant normalization. And it's convenient for checking that various properties of our theory are Lorentz invariant, but it's not so nice in the fact that the overlap between these states is not just a delta function.
So the Lorentz invariance also depends on the Lorentz property of the delta function.
That's right, yeah. Okay.
So you said like other textbooks use unit normalization. That means they normalize to like a delta sign, like a Dirac delta, not a Coherent delta.
So the unit normalization, which I will not use, is P K equals delta P minus K. That's what I'm calling unit normalization. And several of the textbooks I refer to use this one. Some use this one. Okay. So those are our one particle states. We can repeat this process. And act on our one particle states with the creation operator again, as many times as we like to get n particle states. And we'll denote these n particle states as K1 up to Kn. And it'll also show in tutorial tomorrow, it's almost the same argument, that these states have total momentum, K1 plus everything up to Kn, and total energy. It's just the sum of the energies of the individual particles. One comment about these n particle states is that all of these operators commute. Which means I can exchange the labels of any of the particles over here without changing the state. So these particles are bosons. And you'll look at that property in a bit more detail in a tutorial later in the week.
Don?
Yes?
So in this relation, you mean with the zero vector? You mean
Zero.
n zero vectors?
The zero?
Yeah.
This is the
one
vacuum
or is
state.
n zero vectors? Because, I mean, it's like have a state vector in n dimensions in the left-hand side, and the right you have one-dimensional vector.
Oh, so
Is
this.
it some product of n vectors?
So what I mean here is this is a state with n particles. And the momentum of the n particles momentum K1, K2, up through Kn. Does that answer the question?
Then,
Yes,
now we found out that these particles behave like bosons.
that's right.
And I was just wondering, like, when we wrote down the Lagrangian, the prime coordinate, okay, we just we wanted to write the theory for a scalar, for scalar particles, and so we imposed the condition that phi tactor equals phi,
That's right.
and that's the only condition we put for the scalars, right? And now we found that they are bosons.
We also impose commutation relations between phi and pi instead of anti-commutation relations.
Right. Okay.
We would have run into problems if we tried to impose anti-commutation relations, as you'll look at
So
in
we
more
use
detail
our knowledge
later.
of scalars and polars.
We did, but we didn't really have a choice, which you'll show in tutorial later.
Dan, right in that ket over there with the n p vectors,
Yeah.
is it a tensor n-fold tensor product or not?
So this, these are just,
There is no tensor.
there's no tensor product.
I think what she means is that it's a symmetrized tensor product. of all the one-particle states with K1, K2, K3. So the Hilbert space on the right-hand side, the zero is actually an infinite number of zeros.
Oh, yeah, right. You can, yeah, think about this as. So we're no longer in just a Hilbert space. It's a Fock space. So it's a sum of arbitrarily large number of Hilbert spaces. One other comment about these n particle states is that the normal ordered Hamiltonian commutes with the number operator, where the number operator just counts the number of particles So if we want to count the number of particles, we just integrate over all of the momenta. A dagger, K, AK. But this is basically just the same operator as the Hamiltonian, just without the extra factor of E. So this counts the number of particles, and basically because it's the same, it's basically the same operator, so we can it's closely related operator. So we can not hard to show that these commute. So particle number is conserved. So this theory doesn't quite fit the first motivation I gave you yesterday for why we should study quantum field theory. But this is a particular property of the fact that we have a free theory. So there's really no interactions here. So this theory conserves particle number, but it's a special property of this theory. All right, so everything I said so far has been in the Schrodinger picture. It's often useful to switch to the Heisenberg picture. So let me just briefly go over how that works. So in the Heisenberg picture, the operators become time dependent. And as you all know, time dependence is just e to the I ht times the operator in the Schrodinger picture, e to the minus I ht. And so if we want to figure out how our creation and annihilation operators evolve with time, we can write the Heisenberg picture creation or annihilation operator as AP of t, and this is just e to the I ht AP e to the minus I ht. And to compute this, we need the commutator of h with AP. And we can show this is equal to minus EP, AP. And then using the relation e to the x y e to the minus x equals y plus xy plus half x with xy, etc. You can show that this is equal to e to the minus I EP t times AP. And same thing for the creation operator, except we just get a plus sign in the exponent. So, you can plug those results back into our formula for the field operator to find the Heisenberg picture field operator, phi of x and t. And that's just integral d through p over 2 pi cubed 2 EP. AP, where since I'm not writing AP of t, this is just, again, the Schrodinger picture operator. And I'll pull out the time dependence we computed. E to the minus I p dot x plus AP dagger e to the plus I p dot x. And so this formula should look very familiar. This is basically the formula we derived when we solved the classical Line-Gordon equation, except now we're interpreting it as an operator equation. So this is back in the Lorentz invariant form we had yesterday. But there's still a hint of Lorentz non-invariance, because if we want to write the commutation relations in the Heisenberg picture, we need to write equal time commutation relations. So time, again, plays a special role. In the way we're thinking about the theory, even though the theory is actually Lorentz invariant. So equal time commutation relations mean that these field operators just satisfy the same commutation relations we had before if we evaluate phi and pi at the same time. And as before, phi of x t, phi of y t is 0, as is pi of x t and pi of y t. So we want to make sure our theory is causal. So because there's this seemingly non-Lorentz invariant property of our theory, it's not immediately obvious that our theory will remain causal. So let's check that. So what do we mean by causal? Causal means that we'll require that any two operators in the Heisenberg picture commute whenever x minus y squared is negative, that is when x and y are space-like. Okay, so this ensures that a measurement at x can affect y or vice versa if x and y are space-like.
I'm done. That gives a hint of non-Lorentz invariant because we are treating t and the space variables as separately. In the equal time commutation relations?
Equal time commutation relations, yeah. So these, yeah. So we have, yeah, we're treating space and time differently, right? So here this is a delta function that depends on x only.
And before, when we had written this commutation relations, we had implicitly assumed equal time, right?
So before we were in the Schrodinger picture, so before our operators were time independent, so it didn't matter what time we evaluate that. Okay. So simplest operators we can consider are just phi. So let's compute the commutator of phi of x with phi of y, which I'll denote as delta. Okay. So this is, given our results up here, integral d3p over 2 pi cubed 2ep times e to the minus I p dot x minus y minus e to the I p dot x minus y. So a few comments about this result. So first of all, we notice that it's Lorentz invariant. So that's a good sign. This is our Lorentz invariant measure. These are all 4 vectors up here. So everything is Lorentz invariant. It's a number, not an operator. So there's no operators in this last equation. And this, again, is a property just of the free theory. If we tried to compute the same thing in an interacting theory, we would have operators down here. But in this case, it's just a number. Next thing we notice is that it vanishes for space-like separations. So let's suppose that let's look at the space-like case. And if we choose a frame where x naught equals y naught, then what we're left with is delta gives us this integral of e to the plus I p dot x minus y minus e to the minus I p dot x minus y And so these two terms are almost the same. If we take p to minus p, like we did yesterday on this term, the measure doesn't change. All that happens is we flip the sign in this exponent, and then we get e to the plus ip dot x minus y minus e to the plus ip x minus y. So this is equal to 0. So that's good. These operators commute as long as x and y are spacelike. This argument doesn't work, though, if x and y are timelike. And I'll fill that argument in a bit more in a few minutes. Okay. So let's try to understand this result a bit more. Why is this 0? So to do that, let's look at a different but related quantity, the amplitude to propagate from x to y, which I'll denote as d of x minus y. And I'll define this to be the amplitude to propagate, for a particle to propagate from y to x. Okay. And so I can write this. If we write these in terms of the creation and annihilation operators as d3p over 2 pi cubed 2 ep integral d3k for 2 pi cubed 2 ek times e to the minus ip dot x plus ik dot y times 0 ap ak dagger 0. So this just comes from plugging in the top formula on the second board up there into here. And then we know this thing here by using the commutation relations for AP and AK is proportional to the delta function, P minus K. And the coefficient will cancel out one of these denominators. So this gives us the integral d3p over 2 pi cubed 2 EP. So the coefficient cancels out one of the denominators. The integral over k will set p equal to k. And we're left with e to the minus ip x minus y. Okay. So let's evaluate this for the case where x and y are space-like. So again, we're going to set x naught equal to y naught. And let's call x minus y r. Okay. So in that case, dx minus y becomes integral d3p over 2 pi cubed to ep e to the I p dot r. Which can be shown is just a Bessel function. So this is m over 4 pi squared r times a Bessel function. This is in particular the modified Bessel function of the second kind. It's a 4, I believe it's 4 pi squared, but that's what I have in my notes, but I could double check. Here, so there's pi cubed here. And so I guess from doing the angular integral, we should get 1 factor of pi. Yeah, so that makes sense that it's a pi squared. So the particular form of this is not particularly important, and it's not particularly easy to go from here to here. Well, it's not terribly difficult, but not worth our time going through it in class. The main point is that this is not 0. It goes to 0 very rapidly as r becomes large. This goes like 1 over r to 3/2 e to the minus mr if r is large for fixed m, but it's not 0. So is this a problem for causality? Not necessarily. So we showed that measurements at x can't affect y. But here we showed that the amplitude for a particle to propagate from x to y is not 0, even if x and y are space-like. So that's perhaps surprising. So what's going on here? So we're looking at 2 points outside the light cone. Here's x. Here's y. And we showed that 5x, 5y, which is just d of x minus y minus d of y minus x, is 0. So what this is saying is that the amplitude for a particle to propagate from x to y exactly cancels the amplitude for the particle to propagate from y to x. And if we repeated the same calculation for a complex scalar field where the particle and antiparticle were distinct, what we'd find is that the amplitude for a particle to propagate from x to y canceled the amplitude for an antiparticle to propagate from y to x. So there's even though the theory is causal, it's a lot more of a a delicate cancellation than we might have first guessed. So there's some interesting physics going on outside of the light cone. Okay, so that's what's happening outside the light cone. Let's examine this function in a bit more detail inside the light cone. This is going to play an important role later. So we'll be interested in one of the simplest questions we can ask is what's the amplitude for a particle to propagate from one point to another? And so that is going to be a building block from which we can, which we'll use when we ask more complicated questions. Yes.
So what this is saying is that on average, only on average, particle goes from X to Y, it'll be replaced by one that went the opposite way.
So this is saying that the amplitudes for a particle to go from X to Y exactly cancels the amplitude for the particle to go from Y to X. So there is zero probability that you will measure a particle going from X to Y if X and Y are space-like. Okay. All right, so what's going on inside the light cone? So let's look at delta x minus y inside the light cone. So we'll do some manipulations that at first look strange, but we'll see the point of them in just a few minutes. So just rewrite what we had before. Okay, so the first thing I'm going to do is bring in this factor of 2EP. And if you remember, so we defined P naught to be equal to EP, so I'm just going to explicitly write that here. And the other term, I want to flip this sign, and I'm going to do that as follows. So I'm going to write this as plus 1 over 2 minus 2EP. So that's that sign. And I'm going to write this exponential. I'm going to flip this sign, sorry, as follows, where instead of evaluating P naught at EP, I'm going to evaluate it at minus EP. Okay. And so why am I allowed to do that? So it's the same argument we've made several times now, that if we take P to minus P, the 3-vector P to minus P, we don't change anything here. We don't change this. So we can just flip the sign of this 3-vector P. And so this, going backwards from here to here, we see that the signs, we flip the sign twice in the 0 component, and the sign of the spatial components, we can flip it well. Okay. So, see?
The first term, the exponents, do you want that to be a minus?
This?
Yes.
Yes, I want this to be a minus. So we started out with a minus. I didn't do anything to it. Minus. Are you asking about this, sir?
Yeah.
The sign? Yes, this should be a minus. I believe.
I think that's
Yeah, it's that. It's basically, it says minus on here. Which the origin of that can be traced back to that minus sign.
Yeah. So did you write the E as a denominator, or I'm seeing that wrong?
This is 1 over 2e.
Time. Okay.
This is 1 over minus 2e.
that is e to the power minus I, or we just flip p to minus p.
I didn't do anything to this first term.
There, right.
This term,
You flip p to minus p.
I flipped I flipped the sign.
Okay.
Yeah. And I'm evaluating it at p naught equals minus ep. Okay. So this is very unusual. I'm going to do one more unusual thing, and then we'll see what the point of it was. So let's look at, assume that x naught is greater than y naught. So this next equation is only going to be valid in that case. Write this as an integral over the spatial part. I'm also going to insert an integral over the 0 component of p. And I can do that as follows. Where now I'm going to treat p naught as a complex variable and integrate over a particular contour. So this denominator here, I can write it as p naught squared minus ep squared. And so in the complex p naught plane, I'm going to integrate along this following contour. So here, this is the point minus EP. This is the point plus EP. And I'm going to integrate, go just around both of the poles above them, and close my contour here. Okay, so I just did a whole lot of things at once, so let me take a step back and try to explain what we did. So it's probably easiest to see where this comes from by trying to go backwards. So this contour, so here we're integrating along the real part of P. This dotted part doesn't contribute anything if x naught is greater than y naught, because this exponential here, if the imaginary part of P naught is negative and large, then this exponential wins over anything else. So this part doesn't contribute. So this is just an integral along here, along this contour. And we're enclosing two poles at where, so there's a pole at when P naught is equal to plus or minus EP. And the terms here just come from the residues at plus EP and minus EP. Okay. So going from here to here is probably a lot easier to do than going the other way. And any questions about that? Okay.
So effectively, I mean, the integration you just described is going backwards, right? Like
Yeah, so I described how to go from this line to that line. So why would we do this? And what's the interpretation of what we've done? So okay, so I'm going to rename the quantity I just wrote down, delta R, where R here stands for retarded, of x minus y. And so that's because the last step is only valid when x naught is greater than y naught. I'm going to explicitly write that here. And so we found that that's equal to this quantity, 5x commutator with 5y. And I can put in these vacuum expectation value because this is just a number, so it doesn't change anything there. And we found that this was equal to the integral along this contour, which I'll call CR of d4p over 2 pi cubed I over p squared minus m squared e to the minus ip dot x minus y. So I'll just bring that I in the denominator to the numerator. Cost of a minus sign. Okay, so what is this? So this quantity here is a Green's function for the Klein-Gordon operator.
So you want 2 pi 4?
Yeah, thank you. Should be 4. Okay, so this is a Green's function for the Klein-Gordon operator. So this operator here is a differential operator that when we acted on phi would give us a Klein-Gordon equation. So I'm just referring to this as the Klein-Gordon operator. And if we act with this operator on this function here, what we get is the integral d4p over 2 pi to the 4th I over p squared minus m squared. This just brings down a factor of minus p squared plus m squared e to the minus ip dot x minus y. These factors cancel. Well, that gives a minus sign. So this is equal to minus I d4p over 2 pi to the 4th. Same contour e to the minus I p dot x minus y, which is just minus I delta x minus y. Okay. So can anyone tell me where I used the contour in this derivation?
Denominator square minus m square.
The contour. Did the contour play any role here?
At the poles, you have to shift them up or down.
Shift them up or down, but what if I'd shift them down instead of, or? I looked at a different contour that went around the poles in a different direction, say below them. Anything change about this derivation?
No, you have the pluses. In your exponential.
In exponential? So imagine I tried to repeat the same derivation, but changed the contour where I went around the poles in a different direction. Same integrand. So here, I just acted with this on that. So that didn't depend on the contour. this step, I just canceled off things, didn't depend on the contour, and then I did an so there's no poles left here. So it doesn't matter which way I go around the poles here. So at no point did I use the contour. So this means that this is a Green's function for this operator. And so I'm over time. I think we'll come back to this tomorrow. And what we're going to do tomorrow is noting the fact that it didn't matter which way we go around the contours. We're going to look at the other Green's functions, which are closely related to this except for the contours, and see how the contours affects the physical interpretation of these Green's functions. They are relevant for imposing different boundary conditions, and there's one particular choice of how we can go around these poles that will be useful for us later in the course. So that's what we'll do tomorrow.